Hi, Alexei.
I don't think I hear you.
Oh, do you now? Do you hear me now?
Yes.
Okay.
I just have some problems with my Ubuntu. It always causes some problems. I think it's getting a bit dim, so let me just turn on lights. I'll be right back.
Yeah, sure. Yeah, so see, I'm missing my beautiful bookshelf today because I went to the office.
Yeah, I noticed that background is different. So I was going to ask you about those books.
Yeah. There's a lot of sci-fi there. Well, unsurprisingly, I guess. But then the quality of Wi-Fi is higher in the office, so here we are.
Mm-hmm. So is it easy for you to go to the office?
It is. I mean, so I work in Paris and then I live in Paris also. So in principle, I could even go to the office every day. But like after a year and a half of COVID, that just seems like a very foreign idea to me.
But in terms of getting in the office, do you just show up and enter the office? Or
yep. We actually have plenty of people here. I mean, right now we are in a flexible policy, like people can work from home or from the office, but we have plenty of people who show up anyway. Mm-hmm. The cafeteria is not bad, so that's strong incentive.
Yeah, so we have something similar, so we can just show up in the office and we need to register in advance. So there is a special app that we use. So
we used to do that.
Right now you don't do this.
No, not anymore. Actually, yeah, you said you're based in Berlin, right?
Yes, that's right.
Yeah, so I wonder if the COVID situation is different there from France.
It probably depends on the company. So in our building where our office is, there are two companies. And for the other company, the rules are different.
Okay, so yeah, that seems very you specific then.
Yeah, so it's just we use one app, and I don't know if they use an app, but they have to come to the guard and show them something, like they have a vaccine or something like this.
Okay. I think in France, okay, so it depends on your occupation, but basically in kind of regular office jobs, legally they cannot like make us get vaccinated, you know what I mean? So that's why they cannot require like COVID passes. Like you're encouraged to do it and you're supposed to wear a mask around the office, but that's as far as they can legally go.
Mm-hmm. Yeah. Okay, but tell me about your books. So what kind of books do you have there?
Well, see, it would be a lot easier if I had them with me. Well, there's a lot of sci-fi, as I said, like Robert Heinlein is a favorite. So there's him. I recently got into Terry Pratchett. That's more fantasy, I guess, but that was my lockdown reading or lockdown number one. And then I used to be a physicist, so I still have a ton of physics books, left over from those days.
So which language are these books in? French, English?
Mostly in English because, so my French is kind of a work in progress still. I mean, I'm supposed to have a good enough level to apply for French nationality. Like that's what I'm doing right now. But honestly, when I try reading fiction in French, there are just so many words that I would never come across in my real life that it's just exhausting. Yeah.
It happens to me when I read books in English.
I see. Yeah, I thought you were about to say German.
No, German for me, like for German, it's 95% of the words are like that. Okay, what is this long word? And actually, even in Russian, when I read books, sometimes I come across words that I only see in books. And
and then you don't know how to pronounce them. I've had that happen.
Yeah, exactly.
And that's always a bit embarrassing. Like I know what it means. I don't know where to put the stress.
Yeah. Okay. I think we're ready to start. So what I'll do now first is I'll just share the slides. It will take a minute. I'll just introduce the community and then it will be your turn.
Okay, sure.
So let me share my screen. I think that's us. So there is some delay between us speaking and YouTube. Anyways, so let me start. So hi, everyone. Thanks for joining us today. This event is brought to you by Data Talks Club, which is a community of people who love data. We have weekly events, and this event is one of such events. There is a link in the description. You can click on this and see and look at all the events we have in our schedule. And there in this link, you'll also find a link to our Google Calendar. So if you want to subscribe to all our events, to every event we will have. That's the link you want. And then, of course, there is this button under the video. You should click on this if you want to stay up to date with all our videos. And I think I saw some stats that 55% of people who are watching videos are not subscribed. So I think you should fix that. And then we have an awesome Slack community. There is also a link in the description, so you can join us and talk about data-related things. And then finally, during today's presentation, you can ask any question you want. There is a link in the live chat. Click on this, ask your question, and then at the end, we will cover these questions. That's all from me. And Olga, now the floor is yours.
Thank you. Okay, so this is supposed to work this time.
Let's hope so. Great.
Okay, so you see the slides.
Yes.
Perfect. Okay, so hi everyone. My name is Olga Petrova, and today I will talk to you about NLP, kind of in general, and transformer, like the transformer architecture in particular. But before I get into that, I just want to, say a few words about myself. So right now I'm working as a product manager for AI platform as a service products at Scaleway. And Scaleway, in case you don't know, is a European cloud provider that is originating from France. So personally, I'm based in Paris. But okay, in case you're wondering why is a product manager talking to you about, something rather technical, I actually used to be a machine learning engineer, also at Scaleway for a couple of years before making the switch to product. And before that, I used to work as a physicist. So I did that in France, Germany, and in the United States before that. The reason why I mention it is that whenever I give a talk, like physics to machine learning is a very common career path. So usually there are other people in the audience who either are doing it or have already done it. So if you have any questions about that, feel free to ask those in the end as well. And before we move on to NLP, I just have my 5 seconds of shameless safe promotion. So, when I don't do machine learning, I paint. So recently I have started a series of paintings of dinosaurs in kind of classical Renaissance portraits. So if you're interested in that, feel free to visit my website, olgapaints.net. Okay, so now coming back to natural language processing. So here's the outline of the talk. The first part is going to be very brief, but also very introductory. It is mostly meant for people who maybe don't work in NLP, like if you work in computer vision, or if you are more used to structured data, this would be helpful. And we'll kind of quickly move past that and get into recurrent neural networks, the attention mechanism, and finally the transformer architecture. Okay, so here is the very basic introduction that I promised. How do we represent words in NLP? So a lot of my examples have to do with cats and dogs because I happen to have one of each. So let's say I have a sentence, I play with my dog, and I want to use that as input to a machine learning model. So of course, inputs should come in the form of vectors or matrices. And when it comes to images, this is very simple. So again, a picture of my dog. This can be represented as a matrix very naturally from the computer point of view. And the same can be said about structured data. When it comes to like human language phrases, it's not necessarily as straightforward. So how can we convert a sentence like I play with my dog into numerical values? And again, if you work in NLP, I'm sure you're well familiar with this. But just in case you don't, basically here we have a phrase that contains 6 different words. I mean, I will say that a dot is a word for my purposes. So we have a dictionary of 6 elements, and each of those can be represented by a one hot encoded vector with dimensionality equal to 6. So the reason why we do it that way is that, if we do that, then each of the words is going to be linearly independent from the rest. And that is to say that you cannot represent, say, the word dog by some sort of clever combination of the other, 5 words in your dictionary. So that's kind of the good thing about one-hot encoding. However, if you want to increase your vocabulary size, say you also want to play with your cat sometimes, if you want to represent just this additional words, you actually have to grow the dimensionality of your input vectors by 1. You go from 6 to 7, and then of course a normal dictionary will include many, many, many more words. So we end up arriving at a very high dimensional input vector. So this actually brings me to word embeddings, but before we do that, I want to mention something about tokens, because kind of throughout my talk, I will probably use like words and token, maybe element also kind of interchangeably. So tokens are just like another pre-processing step, and you can actually say that every word in a sentence and every punctuation mark is a token in itself. What is done more often is that you use subwords tokenization, where you might split your word into multiple tokens. There's some benefits to this. The main benefit, I would say, is the fact that this way you have fewer unknown words, because of course, if you have a word in your sentence that is not part of your vocabulary, there's simply no way to represent it as an input. So typically you would default to an unknown token. And subword tokenization kind of helps with that not happening as often. Just for the rest of my talk, to keep things simple, whenever I say token, I just mean a single word or a single punctuation mark. So we'll just keep it there. Okay, so this was one-hot encoding, and here again, a very kind of pet-focused example with a cat, dog, kitten, and puppy. So here we have vocabulary size n, whatever that is. It could be 4, it could be 4 million, we don't care. But in human language, we have relationships between words, such as a dog is to a puppy, as a cat is to a kitten, and one-hot encoded vectors don't help us with recording those relations at all. Like by definition, they're linearly independent. So there is no relationships between words that can be available. So what we can do here is we can go from this high dimensional representation to a lower dimensional representation of the words. So we go from n to m, and m here could be 3, but the point is that m is much lower than your vocabulary size. Now, when you do that, your vectors, mathematically, they cannot be linearly independent anymore. So the words are kind of forced to group together, in a sense. And the idea is that you want to group them together in some way that is meaningful. So some way that captures the meaning of the words or the relationships between words. And this can be done. So actually in this toy example that I have here, where we went from n equal to 4 to m equal to 3, if you examine the vectors that I kind of wrote out by hand, you will see that if we subtract puppy from a dog, we get the same thing as we would get if we subtracted kitten from a cat. So we actually managed to kind of encode this, parent-child relationship in this vector representation. So in order to have word embeddings, of course, this isn't something that is done by hand. In order to arrive at a word embedding matrix, again, you do it via machine learning. So there are multiple ways of doing this, but the basic idea is that you have a kind of encoder-decoder architecture where your encoder has a bottleneck layer at the output. So you start with a high-dimensional input, then you're going to kind of shrink, and then in the end, you arrive at a lower dimensional output of the encoder, which you would then feed into the decoder, just so that you have a model that you can train. There are different machine learning tasks that you can train this encoder on. This one that is used often is language modeling. You can also use others. This is for people who like linear algebra. If you don't, I'll just say that, of course, when we do this, some information gets lost in the process because we started with linearly independent vectors, and we arrive at vectors that are no longer linearly independent. However, we lose some but gain some. First of all, we arrive at a much lower dimensional representation, which is nice. Second, words actually have hopefully meaningful relationships between them in this representation. So this embedding step, this could be part of your machine learning model that you are training from scratch, but because it takes really a lot of resources to train something like that, most typically in practice, you use pre-trained embeddings. So I will mention one that is based on transformers in the end. The ones that came before that, the most well-known are Word2Vec, and there's Cloud, and you can take them just pre-trained, feed your words tokens into them and get some dense vectors out. Okay, so this was a very brief introduction into the field of natural language processing. And if you're curious about tokenization or word embeddings, there are a couple of blog posts that I enjoyed reading when I was learning about this. And now let's move on to recurrent neural networks. And again, if you work in NLP, it is very likely that you're familiar with them. But I just want to highlight certain features of RNNs that actually turn out to be more bugs than features and how those can be fixed. Now, when I talk about RNNs, I like to use sequence-to-sequence models as an example, but just a little disclaimer, not all sequence-to-sequence models are belong to the domain of NLP, and also not all NLP models are sequence-to-sequence, but they're common enough, and also they are very kind of illustrative for the purposes of talking about RNNs. So a sequence-to-sequence model basically just means that your input is a sequence and the output is also a sequence. So the common examples here include language modeling, question answering, machine translation, etc. So the example that I will be using here is that of machine translation, where the input sequence is a sentence in French, je suis étudiant, and the output sentence is I am a student. So the translation of the French phrase into English. So a couple of takeaways. What I mean by sequence, there are typically multiple elements in it. So for NLP, this would mean, say, multiple tokens. And what's also important is that the order of the elements in the sequence matters. Okay, so if you decide to look up RNNs on Wikipedia, you arrive at a definition that is, correct, but maybe not very helpful if this is your first time looking into RNNs. So recurrent neural network is a class of artificial neural networks. Okay, that's good. Where connections between nodes form a directed graph along a temporal sequence. So if this doesn't make sense to you when I say it this way, it should make sense to you shortly. Like, this is going to be my goal for the next few slides. This is a kind of schematic that I did of an RNN meant for a sequence-to-sequence problem. So we'll talk about kind of every part of it separately. So we have an encoder and we have a decoder. So this is an architecture that you also often see in computer vision if you're coming from that field. So basically, you want to encode something, arrive at some sort of representation that makes sense for a problem, and then decode it into typically something else. So in this case, you encode a French sentence into something that has meaning to the network, and then you decode that meaning into an English phrase. So the input sequence gets fed as input into the encoder, and the output sequence is the English phrase. Now, when I say inputs, I'm actually talking about word embeddings. So I'm just going to assume that you have already taken your one-hot encoded tokens and put them through Word2Vec or whatever. So your inputs are word embeddings. Now, because if you want to go from word embeddings back to actual words, this is not in general a one-to-one correspondence. Your outputs will typically have a different form. So usually you would have an output layer that has the dimensionality of your dictionary size. And that will be a softmax layer that is going to tell you what is the probability of each word being kind of the right element of the sequence. Okay, so again, inputs, je suis étudiant, and we are going to take them one by one and feed them through the encoder. So we take the first one, je, and we put it through the encoder, and we arrive at a hidden state. So that's what H E1 stands for, so H hidden, E encoder. Now, once we get that, we feed that as input again into the encoder. And we also feed, at the same time, we also feed the second element of the input sequence, SWI, also into the encoder. So once we do that, we have another second hidden state that gets produced by the encoder, and we feed that back into the encoder together with the third element of the sequence. And then once we're done with the entire input sequence, we arrive at our final hidden state that is referred to as the context vector. So if you think about it, because of the way that we've done it, we processed an element, we send that information back into the network together with the new element. Once we process that, we have done it again. So actually the context vector has information from all of the elements in the sequence. So it is supposed to contain the meaning of the whole input sequence. So sometimes it works great, other times, and we'll get to an example that doesn't necessarily work so well, but that's the idea. Coming back to that scary-looking Wikipedia definition, the temporal direction is basically this, because here, of course, it's not that there are 3 encoders that I'm using. It's actually the same encoder network that I'm just feeding elements into one by one. Okay, so once we have the context vector, that's going to be our first input into the decoder. And the decoder is going to have 2 outputs. So the first one will be kind of the first element of the output sequence. So as I said, actually, it's not going to be the first element. It's probably going to be a softmax layer that is going to tell you, this is how likely each of these words is to be the first element of the sequence. And you can keep just the single most likely one, or you can keep, I don't know, top 3 or top 5 and just construct several combinations. And then in the end, you can pick one with the highest overall probability. But again, just for simplicity, I'm going to say that at every step, you're going to pick the most probable element of the sequence. And that's one of your outputs. The other output of the decoder is, again, a hidden state. So far, you have only output I. So you're not done yet. So you feed both I and the hidden state back into the decoder. You get a new hidden state and the second element of the sequence M. You feed M and the previous hidden state into the decoder, and you just keep on going until you reach a token that is called end of sentence token. So if you have a high probability of end of sentence token being your kind of next words, that means that you're probably done there. Like your translation job is complete. Okay, well, before I switch to the next slide, just give you a second. And here, the word recurrent probably also makes sense just from looking at the schema, because basically we feed elements into the network over and over again. Now, does this really work? It actually works, surprisingly, perhaps well. So if you use Google Translate a lot, like I do, maybe you noticed that around 2016, things got better. And part of the reason why it got better is that they started using RNNs behind hood. I don't know if they have switched to transformers since, but basically, yes, RNNs are really pretty good for doing NLP. However, they don't come without challenges. So the first challenge is, well, it has to do with how they are. I mean, a recurrent network is by definition non-parallelizable because you have to feed elements one at a time. So they kind of depend, each element depends on its previous step. So because these steps are not, they cannot be treated separately, you cannot parallelize them easily. Now, the second catch has to do with that context vector that I mentioned. So you're relying on a fixed length context vector to capture the full input sequence. So sometimes this can work well, other times not so much. So if your input sequence is I'm a student, then you're probably good to go. If your input sentence comes from, some sort of like obscure Russian novel where they love to use long sentences, this won't work so well. So actually, to come up with a counterexample, I just Googled like long sentence, something like this, just because I wanted to get one in English. And that's the example. It was a wrong number that started it, the telephone ringing 3 times in the dead of night, and the voice on the other end asking for someone he was not. So let's say this is your input sequence, and you want to encode that as a 512-dimensional vector. Well, good luck with that. So for this second tool that I just explained here, there is a solution, and that solution comes in the form of the attention mechanism. Okay, so what is the attention mechanism? On the left here, this is basically the schema that we had before. We have the encoder, we have the decoder, and it is only the last hidden state, once we're done with the entire input sequence, that gets passed on as input to the decoder. Now, instead of that, we can have a very similar architecture where we're actually going to take all of the intermediate hidden states that come out of the encoder and feed all of them as inputs to the decoder. So that's pretty much it. That's how attention works. Inside the decoder, you are now going to have something like a softmax layer that is going to, at every step, just look at what is the most important part of the sequence. So if you're doing translation, let's say you have this je suis étudiant, and you're trying to output the second element of the sequence, which is M. So when you're processing that, you want to look at all of the hidden states that came from your input sequence, and if the decoder has been trained correctly, chances are most of the attention will be spent on suis, which is French for M. So that's the kind of idea behind attention. You take all of the hidden states and you use all of them. And this attention mechanism is actually the central part of the transformer architecture. And again, before we move on to transformers, here are a couple of links. So again, these links are actually about transformers, but they talk a lot about the attention mechanism in general. There's some noise in my office. I hope you can't hear it too well. Okay, that's good. So transformers. In 2017, there was a paper published by Google with the name "Attention is All You Need." And this is an extremely descriptive name for a paper, because literally you just, you take that RNN with attention that I talked about in the previous slide, and you just throw away the RNN and keep the attention. And that's it, you have a transformer, basically. So the basic idea of attention was to pass all of the hidden states as inputs to the decoder. And actually in the transformer architecture, there are now 3 types of attention. So I'm going to list them here in a list. This will make more sense when I show you the schema. But again, you're going to have a decoder and an encoder, and each of those are going to have multiple layers. Now, the output hidden states of the encoder are going to be inputs to all of the layers of the decoder. And this is one of the 3 types of attention, the encoder-decoder attention, that is most similar to the attention that you can have inside RNNs. But it doesn't stop there, because actually so as I said, the encoder itself has multiple layers. So of course, you're going to have intermediate hidden states inside the encoder. And these intermediate hidden states of the encoder are also inputs to other sequence elements encoder layers. This is something called self-attention for the encoder. And I will point out exactly what it is when we look at the schema. So just keep in mind that there is this other type of attention going on. And then the 3rd type of attention is self-attention inside the decoder. So again, all of the intermediate hidden states inside the decoder also get fed into other sequence elements layers of the decoder. So if this makes no sense to you right now, just hold that thought until the next slide, and we'll come right back to it. Okay, so here there are a lot of arrows, and the reason for this many arrows is that there's attention everywhere. So here I have the encoder. And in this example, I have 3 input tokens. So word 1, word 2, word 3. What I refer to as pre-processing, this can be typically a word embedding, this can be a regular word to vec or whatever, just to get from one hot encoding to a dense vector. And in addition, you will have position encoding, because since we throw away the RNN, there's now really no sense of kind of direction in the sequence. So for each of the sequence elements, you want to numerically encode the position of an element in the sequence. So I won't dwell on that too much, but in general, it's fairly straightforward. So once you get down with that pre-processing, once you get down with that pre-processing, you'll move on to the first layer of the encoder. The output of that is going to be some hidden state. This hidden state, of course, gets passed on to the next layer of the encoder. But in addition to that, remember that we have 3 elements being processed in parallel. So each of these 3 elements gets information about the other elements in the sequence. So you process the entire sequence all at once, all in parallel, and through this self-attention blocks inside the architecture, you're going to get the previous hidden states for the other elements in the sequence when you process your element. So the areas that are inside the encoder going from one element to another, that's what is referred to as self-attention. And the self-attention is actually something extremely useful and kind of very innovative. One of the reasons why transformers work so well. Another thing to notice is that this architecture is bidirectional by design. So again, because we process everything completely in parallel, there's really no sense of direction as there was for the kind of vanilla RNN that I mentioned. RNNs can be bidirectional. So the original version wasn't, but you can make them bidirectional, but transformers are always bidirectional. So that's nice. And just to give you an example of why it's nice, there are 2 sentences that I heard in some YouTube video that I watched like a couple of years ago. So I wish I could credit it, but unfortunately I don't remember, what video that was. So let's say you have a sentence that goes like this: the animal did not cross the road because it was too tired. So here, if you were processing the sequence element by element, once you would reach to the word it, you actually wouldn't know if it was an animal or the road, because the sentence could have been instead, the animal did not cross the road because it was too wide. Here we understand that it refers to the road. Whereas in the first one, it refers to the animal. So in order for the network to kind of understand that, it of course has to have information about all of the elements in the sequence, because otherwise it's just it and it doesn't know what it is. So this is where self-attention comes in. And also the fact that it's bidirectional, because if we had a unidirectional, kind of left to right kind of network, then you wouldn't know whether it was the animal or the road until you go to the last word in the sentence. So that's where bidirectional character and self-attention comes in. Okay, now again, the final hidden states of the encoder get passed on as inputs to all of the layers of the decoder. So inside the decoder, you again have multiple layers. Inside you have self-attention, meaning that when you process an element of the decoder, it has the information about the hidden states coming from all of the other elements that the decoder has already produced up to that point. So for the encoder, we're dealing with an input sequence that is already there. We can process all of the elements in parallel. If we're talking about a sequence-to-sequence model where the second sequence gets generated kind of one element at a time, actually the decoding parts of the transformer is going to be done sequentially. So we're going to lose a bit of parallelism there, but oh well. Otherwise, I think that basically wraps up the transformer architecture. So the 3 important takeaways are self-attention inside the encoder. self-attention inside the decoder. This is something that gives you information about context inside the sequence, and of course the encoder-decoder attention. Okay, now how are we doing in time? I guess we're still good. So that brings us to BERT, the contextualized word embeddings. And I spent so much time talking about self-attention and how it brings context, kind of exactly because I thought I was going to talk about contextualized word embeddings. So just a little reminder of what word embeddings are. We start with these sparse vectors, the one-hot encoded vectors, and we want to arrive at dense vectors that have some sort of meaning when it comes to representing tokens or words. Now, as we know from our everyday life, meaning of a word very often depends on the context, so the surrounding words. Now, you know that self-attention transformers processes context when encoding a token. So if you're just training a regular machine learning model to get a word embedding matrix, typically there's not much in the way of context there. You take an element and that single element gets transformed into a dense vector. This is not the case with transformers, because you would feed the entire sequence as an input, and for every element of the sequence, you would get a separate dense representation. So that is due to self-attention and having context. Now, can we just take the transformer encoder, throw away the decoder, and use that to embed words? So it sounds, when I phrase it as a question, kind of sounds like there's a catch. Actually, there's no catch. This is exactly what BERT is. So BERT stands for bidirectional encoder representations from transformers. So we literally take the encoder, we take the transformer, we pre-train it on some task, two tasks actually in the original BERT, and then we use that as our word embedding matrix. And now instead of word2vec, you can use something like BERT for your NLP tasks. So the original BERT has been pre-trained on two tasks. So one is mask language modeling, and this is a self-supervised task, which is very nice because you don't need any manual annotation. Basically, you take a big text corpus, like all of English language Wikipedia or something like this, and then you're going to take sentences and randomly mask out a few words. This is your input, and your output should be, say the same sentence with the words restored. And because context can actually transcend words, transcend sentences, you might also want to train it on another task, which was done for BERT by Google, I believe. There you would take two sentences and do a binary classification training where if the two sentences are sequential in the text, then say that's a 1. If they are not, if they don't proceed one another, then it's 0. So again, this is just a way to train the network to kind of recognize context from neighboring phrases. And again, some further reading. Well, actually, these two blog posts are the blog posts that I wrote that this talk is kind of based on. And finally, if you want to actually use these things in your own machine learning projects, the library that I recommend comes from the Hugging Face. It's called the Transformers library. So back when I first played with it a couple of years ago, I think it was fully PyTorch based. But they have expanded since then, so they have a lot more things going on now. But there's pre-trained BERT in all sorts of languages, pre-trained transformers, trained on different tasks, and those kinds of goodies. Okay, so this was actually my last slide. And Alexei, so I don't, if the questions are on YouTube, I don't actually have a link to YouTube. So if you could maybe read them.
You will read them. So far, actually, I don't see many questions. So if you want to ask a question, there is a pinned link in the live chat. So please go there, click on this link and ask. And yeah, I have a couple of questions from me in the meantime. So you went through this one-hot encoding, then RNNs and attention transformer and BERT, and every time it became more and more complex, right?
Yeah.
How do we decide where do we need to stop for our task? Like, let's say we have a problem, we want to solve it. Like, do we need to follow them to follow this in sequence? Do we need to start with one-hot encoding, then go to RNN, or we just go directly to BERT and just use it?
Yeah, well, so first of all, about the one-hot encoding and word embeddings. So typically these days you wouldn't even bother with one-hot encoding. You have your text corpus, you have your training data, and you just go straight to word embedding. Now, word embedding could be word-to-vec, just regular, straightforward word embedding, or it could be BERT right away. Let's say BERT. It's not a very light model, let's say. It's a pretty heavy one, like it takes a lot of space in memory. But since then, there have been many lighter versions of BERT available. Usually, the name of the model is some variation of BERT. There's Roberta, which I think is supposed to be some sort of diluted model of BERT. So you can try one of those. But in general, BERT does seem to work better for phrases when the context is important. So I would go straight to that.
And so you talked about machine translation. What are the other good applications, good problems that for which you would start directly with BERT?
So actually, I think in the Huggins Face library, they have this. So they had a bunch of different tasks like question answering, for instance, where they have a pre-trained model. Well, they start with BERT and then they pre-train a model on, Stanford question answering dataset. And there the task is, you have an input sequence that is, some text paragraph, and then you have a question that has to do with the text, and then the output is supposed to be a subset of the paragraph that answers that question. And actually, at the time, I don't know if it's still the case now, but at the time they achieved state-of-the-art performance on that. And actually, there were many more tasks, not just machine translation, not just question answering, where they achieved state-of-the-art performance at the time. So it works pretty well on a lot of these kind of sequence, whether sequence to sequence or sequence to value kind of problems.
Yeah, thanks. And let's say I want to learn more about this. I want to learn more about NLP. I want to use to work on NLP problems. How do I learn that? Do I need to start with follow the path you suggested, like from NLP 101, then RNN, then eventually to BERT, or we can just jump directly into BERT? Like, can we actually do this, or we have to go to follow the sequence?
Well, I would say, if you are coming from a different domain of machine learning, say you only worked in computer vision, or you only worked with structured data and kind of classical machine learning, let's say, I think it's always good to understand what you're doing. So I wouldn't go straight to Hugging Face and just dive into the transformers. I think it's good to understand what is happening under the hood, because actually, the one-hot encoded vectors, you are not going to see them in your projects because most likely you're not going to be training your own word embeddings. You're going to use something pre-trained. But just to understand how you go from text to dense vectors, I think this is something that people should have a clear picture of. Yeah. So I would just start with maybe some short online course that kind of introduces you to NLP before you dive into these things.
Do you have any recommendations?
So the one that, when I was transitioning from physics to deep learning, the thing that helped me the most was the Coursera specialization on, this deep learning specialization on Coursera by Andrew Ng. He has a famous class on machine learning, but then the deep learning specialization is made up of 5 different classes. And one of them, I think it's called sequential models or something like that. And it has to do with NLP. and it takes you through RNNs. And of course, the version of RNN that I showed, it's the most kind of vanilla one. They're having, many things done to improve on that. Although at this point, I mean, if you really want to use transformers, for instance, I feel like you can just kind of have some idea of what an RNN is, what are the problems with RNNs that are being fixed by the transformers, and just kind of skip those fancy RNNs and move to that.
And fancier RNNs like LSTMs and
yeah. Basically, because there was this problem, right, with having before the attention mechanism came around, it was a real problem to encode a long input sequence into a single context vector. So there was this, memory types of things where you would want to go back to some elements before in the sequence and see if they're relevant.
Yeah, I was trying to understand LSTMs like maybe 5 times, like how they really work. And every time, like I thought I found good articles, so I went through those articles, and still I had no clue what's going on there.
So I learned them once in that Andrew and G's class, and I remember they made sense. But honestly, I mean, that guy, just the way he explains things, whatever he says, it always makes sense at the time. But because I haven't used them since then, I have very little memory of that, to be honest.
Okay, yeah, thanks. So let's say if I want to get started with BERT, so like I go to Hugging Face, I get the model, right, the embeddings. So how do I learn? Do you have any problems? Can you recommend any problems that I can use to get started with this, to learn more about this?
Well, so I think what's important to remember is that BERT by itself is just a word embedding. So what you're going to get out of BERT is just a dense vector. And dense vectors are great, except that they make no sense to us humans whatsoever, right? So if you want to actually use BERT in a project, you should think about what is the problem that you're trying to do. Let's say it's, intent recognition could be that, right? Like you could have an input sequence where your user tells you something, you want to just recognize what is the user trying to do, like to know where to transfer them next. So you will actually have to supplement BERT with an additional layer. And that layer could be just something you sit on top of BERT, on top of this word embedding. And this can be a softmax layer where dimensionality is equal to the number of intents that you have. So you definitely have to supplement it, because by itself it's just a word embedding matrix.
Okay, so we have a couple of questions. So maybe I will share my screen so you can also see the questions.
Sure.
Okay, now I'll share my screen. Okay, yes. And by the way, I was checking your website.
Yeah.
With the Mona Dina. That's cool.
Yeah.
Okay, yeah, so there's subscribe. You can subscribe to this website if you want to see more pictures like that. Coming back to the questions, so let's start with this one. Where do you think the future of this field is headed in the next few years? And what about NLP as a whole?
Yep. Well, I feel like to some extent it's always hard to tell, because often you have these kind of breakthroughs that nobody saw coming. Like transformers really transformed the field in a sense. But something that people have been doing since then is just training bigger and bigger transformers, GPT-2, GPT-3, or just take the most complicated network that you have. Because, here on the schemas that I showed, when I said like multiple layers and encoder and decoder, there were like 2 or 3. I think in GPT-3, it's something like 96 layers. And between each of those 96 layers, remember, you have self-attention for the encoder, self-attention for the decoder, and attention from the encoder to the decoder. So those are extremely complicated networks, meaning that they have a ton of trainable parameters. So of course, you have to train them on really a lot of training data. So people have been doing that. I guess for now, I would say it's more of an academic interest, but out of that, you can get some pretty impressive things. Like, for instance, if you train those networks on pieces that include code, then those networks can actually write code. Like you can tell them what to do in, say, your natural language. Like, I want a web page that looks like blah, blah, and has this window. And if the network has been trained on that sort of thing, it will actually just write the code for you.
Yeah, that's amazing. I saw videos on Twitter because I want to, let's say, I want to have a website with for selling dinosaur pictures, and it just boom and makes it. That was amazing. Like it produces valid React code, like the demo I saw, and then you can just put it. Like I don't know how much post processing you will need for that, but the way it looks, it's amazing. So yeah, that's cool. So what do you think about GPT-3 in general? Is it a good thing?
Okay, so I actually, at some point, I wrote an article about how much energy was spent on training it. Well, because so at scale, we would have an very energy efficient data center. So of course, we don't have enough GPUs to train a model like that one because it used, I think, 10,000 like latest generation GPUs, like a cluster of 10,000 GPUs like that, just to train that single model. But basically, you use really a lot of energy on training those kinds of things. But then again, energy also gets spent around on flying, airplanes, things we don't do since COVID started. So, that's not a very strong argument for some people. Now, whether GPT-3 is going to take over the world, no, because in the end, we are still talking about, weak artificial intelligence or like specific artificial intelligence in the sense that it is trained to produce text. Well, it will produce text. That's kind of all there is to it. Of course, it's very impressive what it can do, but once you understand how complex the architecture is and just how much text it was trained on, I feel like it becomes less surprising, like the results that you get.
And it was trained on the common crawl data set, right? So basically the copy of the internet.
I think something like that. Yeah, I remember I had in my notes somewhere what was the size of the dictionary that was used. I think it was like it was either 49 billion like tokens, or it was 490 billion tokens. I mean, it's just, this giant monstrosity. Yeah.
Okay. Yeah, it works surprisingly fast. I mean, as I saw the API, yeah, it's not slow. I mean, considering the size of this model, they somehow managed to make it faster. So that's impressive.
Well, plus that's just inference, right? That's not training.
Yeah,
training
exactly.
is the hard part.
Yeah. So how to deal with long documents and paragraphs?
Okay, so in the original pre-trained BERT, they have some like kind of window size, because of course there is, okay, when you pre-train a model and then you want to use that model, the model was pre-trained on passages of a certain size. So if you use a passage that is longer than the size, I think it gets broken down into pieces. Can't remember how long it was right now. But it was definitely not just a single sentence. So it can take context from, several neighboring phrases, say a small paragraph. So that's not a problem. But if you wanted to take, say, 2 pages of text and get the context from like the entire text all at once, what it means is that for every single element of this input sequence, you want to get information from the other elements of the input sequence feeding back into it. So this is just something that would take a lot longer to train. So there are some limits placed because of that. So it can be done in theory, but in practice, there are limitations.
And why would you want to do work with long documents?
I mean, in principle, again, think back to kind of very existential style novels, right? Where some character is brooding over like their life and, thinking about some like her or him, and you don't know who he or she is until the end of the chapter. So in those kinds of examples, sometimes it's important to know the context from quite far away from where you're currently in the text, or, these. Okay, so I lived in Germany for 3 years. I don't speak much German, but I remember that often the verb goes to the end. So you can have an extremely long sentence and you don't know what is happening until the very end of the phrase. So again, we're not talking about two-page document here, but in general, you do want to have context.
Okay, yeah, thank you. So the next question, is a transformer just a pre-trained model that can take your sequence and go straight to decoding?
So actually, I guess I wonder if by transformer you meant BERT here, because BERT was pre-trained model, but in general, transformer is just an architecture, right? You can you could write your own transformer architecture and network that doesn't even have to be meant for NLP. This can be used for other types of sequential data. And this has actually been done. I believe there have been some applications in time series where they use transformers. And you can just train it from scratch. But yeah, so I think just looking at this question, I think you're probably asking about BERT, because yes, with BERT, that's kind of what you do. You can take a sentence, you can encode it with BERT. BERT doesn't come with a decoder, so you would have to supplement that with, say, an extra layer or an extra, network on top of that, and train that on your task.
But usually you don't want to train it yourself, right?
So this encoder part, the word embedding part, you probably don't. Yeah.
Because you need to have a lot of computing power for that, right?
Yeah, computing power, huge training set.
Exactly. Okay. So next question. I'm new to NLP. Is it expected to always work with dense vectors? Will we always be able to transform sparse data into dense?
Also pretty much. Yep. This sometimes isn't done explicitly, like how I explained it. You start with one hot encoded vectors, and then you do this word embedding, and then these are your dense vectors. Even if you started with one hot encoded vectors as your inputs, what happens inside the network, like what happens inside the encoder, is basically transforming that sparse data into dense intermediate vectors. So often this is done explicitly. And the reason for that is that you already have pre-trained embedding vectors that just saves you time.
Okay, and then I'm looking also at the live chat, and there is a question about your thoughts on NLG. I think NLG stands for Natural Language Generation. I don't know, so correct me if I'm wrong. But what are your thoughts on natural language generation?
I wonder what they mean by that exactly, because what comes into my mind is like language modeling, like generative language modeling. So if we're just talking about that, well, what are my thoughts, on the technical side of it? I think there are a lot of exciting things going on that do require lots of power, lots of training data, but okay, fine. Progress is being made. Now, when it comes to applications, I think that it's likely that certain copywriting tasks or kind of easier coding assignments will probably be automated in the not so distant future.
Nice.
That can actually be nice indeed. Yeah.
Like, for example, take this webinar and turn it into an article. That would be great, right?
Yeah,
an article that we don't need to edit.
Yeah.
Because now if you transcribe, you will need to edit it.
Yeah, I was thinking, what if we just do transcription? But that's true. Yeah.
And then with illustrations, of course.
Right. That could be generated by a GAN. Why not?
Yeah. Okay. So we don't seem to have any more questions. So maybe the last question from me. How can people find you if they have any questions?
Yep. Oh, so unless they want to talk about dinosaurs on portraits, I am on LinkedIn. So it's Olga Petrova. There are many Olga Petrovas on LinkedIn. I'm the one who works at Scaleway. So you can find me there pretty easily. I usually give a link to my LinkedIn in the slides. I'm not sure I did it this time though.
But you'll share the slides, right?
So should I send them to you or?
Yeah, you can send them to me, and then I'll put the link to the description, and then you can I'll include also your LinkedIn profile.
Okay, perfect. Thanks.
Do you have any last words before we wrap up?
The
word of wisdom.
Yeah, that pretty much covered it.
Okay. Okay, I guess that's it. So I don't see any more questions popping up. So I would like to thank you for joining us today, for sharing your knowledge with us, for walking us through the history of NLP in 35 minutes, I think.
I tried. I really tried.
That was pretty dense. And also, I remember we talked about this. You said this presentation was initially for 1.5 hours or something like this.
Yeah.
So that's amazing what you did there. Like you managed to condense this into 35 minutes. That's awesome. Thanks a lot. And thanks everyone for joining us today, for asking questions, for watching this. And yeah, I guess that's all.
Yes, thank you. And thank you for inviting me and organizing this.
Yeah, that's great. So have a great